The topic of this video is Chapter 6.2, Enthalpy and Calorimetry. What is enthalpy? Enthalpy is a defined property of a system. It is a made-up quantity, and it is symbolized by the uppercase letter H. The enthalpy of a system is equal to the sum of the total internal energy and the product of the pressure and volume. What does that mean? I don't really know, and it doesn't really matter because we never talk about the absolute enthalpy of a system. What we talk about is an enthalpy change in a chemical or physical process. Delta H, the final enthalpy minus the initial enthalpy. That's the only enthalpy you're ever going to use. It is essentially Q sub P, which means the heat flow at constant pressure. So when a system undergoes a change in its heat content at constant pressure, that change is defined as the enthalpy. From a chemist's point of view, we can think of the enthalpy as the heat of a reaction in units of kilojoules per mole. Let me give you an example. If I burn 2 moles of hydrogen gas in 1 mole of oxygen gas to form 2 moles of liquid water, the enthalpy change for this process is negative 572 kilojoules per mole of reaction. Now, let's be very clear what this means. It means every time 2 moles of hydrogen gas reacts with 1 mole of oxygen gas to form 2 moles of liquid water, the system loses 572 kilojoules of energy. Per mole of reaction means for that set of coefficients as it's written. Okay? So what we're going to do is use the enthalpy change for a chemical reaction to interconvert between quantities of reactants and products and amount of heat flowing in or out of the system. Okay? By the way, the fact that delta H is negative indicates that that is an exothermic process. As we all know, combustion of hydrogen gas produces heat energy. Heat flows from the system to the surroundings. Here are some examples of the sorts of problems we can do. Consider the combustion of hydrogen, which we just said. How much heat is involved in the production of 1 mole of liquid water? Well, again, we're going to use that negative 572 kilojoules per mole of reaction as a conversion factor. So I'll just start by writing my 1 mole of water. And now I'm going to multiply that by negative 572 kilojoules. But how many moles of water are produced in the reaction as it's written? 2. So that's per 2 moles of water to give me a heat flow of negative 286 kilojoules. Now, it says how much heat is involved in the production of 1 mole of water. If you had simply said the net heat produces 286 kilojoules, that would be fine, but I like putting the negative sign there to remind myself that it's an isothermic process. How much heat is involved when 6.05 grams of hydrogen burns in excess O2? Well, I'm given grams, so of course I'll have to convert that to moles. So 6.05 grams of hydrogen divided by 2 times 1.008 grams per mole. Remember, hydrogen is diatomic, times, again, negative 572 kilojoules. But as we see, as the equation is written, 2 moles of hydrogen gas reacting. So I'll put this over 2 moles of H2 to give me negative 858 kilojoules. Then finally, how much heat would be required to decompose 100.0 grams of water to its elements? Because we are considering the reverse reaction, that is the decomposition of water to hydrogen and oxygen, that will be an endothermic process. So I'll take my 100 grams of water, divide by the molar mass to convert from grams to moles, and multiply this now by positive 572 kilojoules for every 2 moles of water, again because water is in because there's a coefficient of 2, to give me a value of plus 15.9 kilojoules. Okay, now let's talk about calculating when we transfer heat to or from a system. I'm going to take this hypothetical system, this blue box, that has a certain mass and is at a certain initial temperature, T sub I, and that I'm going to transfer heat energy to it from the surroundings. It absorbs the heat energy and the temperature goes up. T final is greater than T initial. To calculate the quantity of heat transferred, we're going to assume that the total amount of heat lost by the surroundings is equal to the total amount of heat gained by the system. And to calculate it, we're going to use a very simple equation that looks like this. Negative Q equals S times M times delta T. Q is the heat lost by the surroundings. S is the specific heat capacity of the system, which I'll talk about in a second in more detail in units of joules per gram per degree Celsius. M is the mass of the system in grams, Delta T is the temperature change of the system, T final minus T initial in degrees Celsius. Now, I know you're all going crazy right now and saying, what? Celsius? Who uses Celsius these days? Well, like I said earlier, anytime you're plugging a temperature into, say, the ideal gas law, it must be in Kelvin, but keep in mind that the temperatures we're dealing with in this unit are temperature differences, T final minus T initial. And because the magnitude of 1 degree Celsius is the same as the magnitude of 1 Kelvin, the temperature difference in degrees Celsius is the same as in degrees Kelvin. So we just use Celsius for convenience. Okay? So let's do some problems using this equation. Oh, first specific heat capacity is defined as the amount of heat energy in joules that it takes to raise the temperature of 1 gram of a substance by 1 degree Celsius or by 1 Kelvin. Here's some examples. Liquid water has a relatively large specific heat capacity, 4.184 joules per gram per degree Celsius, whereas iron, like most metals, has a relatively small specific heat capacity. We can also calculate the molar heat capacity, which is very similar. It is the amount of heat energy in joules needed to raise the temperature of 1 mole of a substance by 1 Kelvin. Well, what's the relationship between grams and moles of a substance? The molar mass. So if I want to convert the specific heat capacity of water to the molar heat capacity, I'll simply take it and multiply it by the molar mass so that grams cancel grams and Celsius cancels Celsius. And for some reason, it's just traditional for the temperature unit in the denominator to be Kelvin rather than Celsius. Okay, let's do a few problems. The specific heat capacity of silver is 0.24 joules per gram per degree Celsius. Calculate the energy needed to raise the temperature of 150 grams of silver from 273 to 298. So I'll do negative Q equals S times M times delta T equals 0.24 joules per gram degree Celsius times 150 grams times 298 Kelvin minus 273 Kelvin. And this gives me a value, negative Q is equal to 9.0 times 10 to the second joules. Why the negative sign? Well, keep in mind that in this process, the surroundings are losing heat energy to the system being defined as the piece of silver. So Q, from the surroundings point of view, is inherently negative. Negative times negative is a positive, and that's consistent with the 9.0 times 10 to the second joules of heat energy being absorbed by the system, not the surroundings. B, calculate the energy needed to raise 1 mole of silver by 1 degree Celsius. As we said before, we'll just use the molar mass. So C is 0.24 joules per gram degree Celsius times 107.87 grams per mole times 1 degree Celsius per 1 Kelvin, or 26 joules per mole Kelvin. It takes 1.25 kilojoules of energy to heat a sample of silver from 12 to 15.2. Calculate the mass of the sample of silver. By the way, I don't think I mentioned this so far this year, but feel free to pause at any point and try the problem yourself, then go back and check and see if you got it right. So, start with my equation, negative Q equals S times M times delta T. Rearrange to isolate mass is negative Q over S times delta T. Because the surroundings are losing heat energy to the system, I'm going to say Q is negative 1250 joules. Now we see the negative works out because that gives us a positive mass, because a negative mass wouldn't make sense. 0.24 joules per gram degree Celsius times 15.2 degrees Celsius minus 12.0 degrees Celsius, which only has 2 sig figs. So that means my mass is 1600 grams of silver. Let's move on. Calorimetry. Calorimetry is an experimental method used to measure heat changes in chemical and physical processes. It can be used to measure the enthalpy change for a chemical reaction. We carry out the change, whether it's chemical or physical, in water in an insulated container. We measure the initial and final temperatures of water or the solution in the container. We assume that the total heat released or absorbed in the process is equal to the total heat absorbed or released, respectively, by the water or solution in the calorimeter. What does this look like? Well, as you will see, we use a very, very simple device called, so to calculate the heat flow, as we said before, we're simply going to use our equation, negative Q equals S times M times delta T. Okay? S is the specific heat capacity of the water solution in the calorimeter. M is the total mass of the water solution in the calorimeter. And delta T is the temperature change undergone by the water solution in the calorimeter. This is what we use. It's called a coffee cup calorimeter. You nest two styrofoam coffee cups inside each other. I usually put a magnetic stir bar at the bottom rather than using this wire ring. You have an insulated stopper at the top and a thermometer or temperature sensor in the center. Remember, the reaction is taking place inside here, and we're measuring the temperature difference of water. So let's see what those problems look like. A 25-gram sample of iron pellets is heated to a certain temperature. The hot iron is then dropped into 100 grams of water at a calorimeter of 22 degrees Celsius. After thermal equilibrium is reached, the final temperature of the iron and hot water is 28.0 degrees Celsius. Okay? Calculate the heat capacity of iron, assuming no heat loss to the surroundings of the calorimeter. Okay? So here's kind of like a little picture. Okay? So I've got my calorimeter with 100 grams of cool water in it, and I've got my 25 grams of hot iron. I will drop it in there. Okay? Heat transfer occurs, thermal equilibrium, everything's at the same temperature. Okay? I am going to start with the assumption that negative Q of iron equals Q of water. So all of the heat lost by the iron as it decreases in temperature is gained by the water as it increases in temperature. I will expand this using my equation. So minus S iron times mass of iron times delta T of iron equals S of water times mass of water times delta T of water. Okay? We know the masses of the iron and the water. We know the initial and final temperatures, so we can calculate the temperature differences. We know the specific heat capacity of water, so there's really only one thing left to solve for, which is the specific heat capacity of iron. So this is negative S water times mass water times delta T water over mass iron times delta T of iron. So plug in negative 4.184 joules per gram degree Celsius times 100.0 grams of water times 28.0 degrees Celsius minus 22.0 degrees Celsius. So delta T water is positive 6.0 degrees Celsius. In the denominator, my mass of iron is 25.0 grams. My delta T of iron is final minus initial temperature. So, sorry, we said the final temperature was 28 degrees Celsius. Minus 254.1 degrees Celsius, or a value of negative 224.1 degrees Celsius. Notice delta T for iron is negative, and that works out because negative times negative is a positive. Specific heat capacities have to be positive. And for the specific heat capacity of iron, we get 0.45 joules per gram degree Celsius. Now, the difference in magnitude of the specific heat capacities is really apparent here, okay? We're assuming that the total amount of heat energy lost by the iron is equal to the total amount of heat energy gained by the water. The iron dropped a huge 224 degrees in temperature, whereas the water only went up 6 degrees in temperature. Why is that? It's because the specific heat capacity of water is so much greater. Let's do one more problem in which we actually deal with a chemical reaction. In a coffee cup calorimeter, we're going to dissolve some ammonium nitrate in water. After dissolution, the final temperature is given, assuming the solution has a heat capacity of 4.184 joules per gram per degree Celsius, and that no heat is lost to the surroundings, can calculate the enthalpy of dissolution of ammonium nitrate. So once again, a little diagram to help. Here's my 1.60 grams of ammonium nitrate. Here's my water. Put it in here, dissolve, dissolve, dissolve. And at the end of the day, we have our ammonium nitrate solution there. Okay? Now, we are going to make the assumption that the heat gained by the dissolution, and notice that because the temperature decreased, that means that the system, the ammonium nitrate dissolving, dissociating, gained heat energy, is equal to the heat lost by the solution in the calorimeter. So I'm going to use the equation, negative Q solution equals S times M times delta T. S, the specific heat capacity of water, is 4.184 joules per gram degree Celsius. The mass is not just the mass of water or of the ammonium nitrate, but the mass of the entire solution. So my 1.60 grams of ammonium nitrate plus my 75.0 grams of water. And my delta T is T final minus T initial, 23.34 degrees Celsius minus 25.00 degrees Celsius, which is negative 1.66 degrees Celsius. Okay? So perform the calculation. Negative Q solution equals negative 532.0 joules. Therefore, Q solution, the heat absorbed by the solution, is equal to plus 532.0 joules. Now, the question wasn't calculate Q, the question was to calculate the enthalpy change. So for that, we'll use delta H is equal to Q over moles, or heat gained by the system, divided by moles of ammonium nitrate dissolved. So to solve that, I will simply do my plus 532.0 kilojoules times, I'm sorry, that was joules, not kilojoules, times 1 kilojoule per 1,000 joules. In the denominator, I have moles of ammonium nitrate, so I'll take the 1.60 grams that I started with and divide that by the molar mass. 1 mole over 80.05 grams. I did the calculation separately to give me a value of plus 26.6 kilojoules per mole as the enthalpy of dissolution of ammonium nitrate. Okay? The fact that it's positive means that it's an endothermic process. Ammonium nitrate solutions get cold as it dissolves, and in fact, this is how cold packs work. If you've ever twisted your ankle while you were playing soccer and you cracked open a cold pack, what you were doing is dissolving ammonium nitrate in water. It lowered the temperature because it's an endothermic process. Okay, and that's all for calorimetry.